Now let's talk a little bit more about what this cross product can represent. Well, the cross product is perpendicular to the original two vectors. So if we connect those original two vectors tail to tail, they're going to form a plane. And that cross product, since it's perpendicular to the plane, can be considered the normal vector to that plane. If I want to find an equation for that plane, well, first I need to create the two vectors. So here's a situation where I have 3 points in a plane. And what I'm going to do first is to determine two vectors that are connected tail to tail by calculating displacement vectors from one point to the other two. So I'll start by calculating P1 to P2. And remember that to calculate that displacement vector, we subtract the coordinates of the first point from the coordinates of the second point. So P1 to P2 would be -3 minus a -5. So we end up with a +2i. And then 2 minus 5, so -3j. And then 7 minus 5, so +2k. Now the other displacement vector will be P1 to P3. And here we get 1 minus a -5, so 6i. 12 minus 5, so 7j. And 6 minus 5, so 1k. So now that I've created these two vectors in the plane, I can calculate their cross product, which will give me the normal vector to the plane. So let's calculate that cross product using our matrix method. So we'll start with ijk, and then P1 to P2 was 2, -3, 2. P1 to P3 was 6, 7, and 1. So my I matrix should be -3, 2, 7, and 1. Remember, we eliminate the row and column associated with I. Then I subtract my J matrix. Remember that negative sign, where the J matrix will be 2, 2, 6, 1. And that's my J matrix. And then finally I add my K matrix, which will be 2, -3, 6, and 7. So remembering to take the difference of my diagonals. So -3 times 1 minus 2 times 7, I. And then again, the difference of my diagonals. 2 minus 12, 2 times 6. And for my k, it will be 2 times 7, or 14, minus a -18. So plus 18 here. So that becomes -3 minus 14 is -17i. Minus 2 minus 12. So 2 minus 12 is -10. Minus that is a +10, j. And then 14 plus 18 is 32k. So this cross product is the vector normal to my plane. So A cross B. To define the plane, I need that cross product, or that normal vector, and a point in the plane. So I'm going to use point P1, -5, 5, 5. And if we remember to find the equation for the plane, we use the coefficients of the components to become the coefficients of my equation. So -17x plus 10y plus 32k, or z, 32z. And that's going to be equal to our dot product calculation. So the -17 times negative 5, the x coordinate times the I component, and then 10 plus 10 times 5, so the j component times the y coordinate, plus 32 times 5. So negative 17 times negative 5, or 17 times 5 plus 10 times 5 plus 32 times 5 just becomes 27, 59 times 5. And that's going to be equal to 295. So the equation for my plane becomes negative 17x plus 10y plus 32z equals 295. Let's look at another piece of information we can get from the cross product. If we look at a parallelogram with a base of a and a height of h, the area of that parallelogram is simply a times h. But h in this parallelogram is also b sine theta, where b is the second side of our parallelogram. So our area could also be computed by taking a times b times the sine of theta. Now, ab sine theta is also the calculation we use for the magnitude of the cross product. So the magnitude of our cross product is actually the area of a parallelogram formed by connecting our two vectors tail to tail. Here's a way we could use that information. Now, to find the area of the triangle with vertices at these 3 points, which are the 3 points we used in the previous example, we just need to calculate the magnitude of our original cross product. If we go back, we can see that our cross product was negative 17i plus 10j plus 32k. Negative 17i plus 10j plus 32k. Now the magnitude of this cross product we find using our super Pythagorean. So the square root of negative 17 squared plus 10 squared plus 32 squared. And if we want to pull out our calculators, first let's move this over so we can see it. And if we pull out our calculator and we take negative 17 and square it and add 10 squared and add 32 squared, and then we take the square root of that, we come up with the number 37.58989, or 37.590. Now that gives me the area of a parallelogram using the two vectors. But I'm not asking for the area of a parallelogram, I'm asking for the area of the triangle. But if I think about it, if I take those 3 points, P1, P2, and P3, the triangle formed by these two vectors is actually half of the parallelogram formed using these two vectors. So the answer to my question then would be 37.590 over 2 for the area of my triangle. So that area would be 1/2 of that square root, or about 18.795. So let's recap. What is the other name for the vector product? Well, it's the cross product. What notation is used for the vector product? We use the big X multiplication sign instead of the dot. What does the vector product represent? Well, the vector product represents a vector that is perpendicular to the plane containing the original two vectors. What's one way to calculate the magnitude of the cross product? Well, we take the magnitude of A times the magnitude of B times the sine of the angle that's created when the two vectors are placed tail to tail. What is the right-hand rule? Well, the right-hand rule tells us which direction our cross product vector is pointing. And we use it by putting the fingers of your right hand so that they curl in the shortest direction from the first vector to the second vector. The cross product is in the same direction that your thumb points. How do we compute the cross product? Well, we set up a series of matrices created off of an original 3x3 matrix using the components of each of our vectors, and the components of our final vector are the determinant of those 2x2 matrices, where the determinant is calculated by subtracting the product of the diagonals, going from left to right minus right to left. What are the cross products of the unit vectors? Well, we determined each of those by using the right-hand rule and the fact that the cross product of two vectors pointing in the same direction is equal to 0. So this table summarizes those cross products. And finally, what is the geometrical meaning of the magnitude of the cross product? Well, the geometrical meaning of the magnitude is that that value is equal to the area of the parallelogram formed when we connect those two original vectors tail to tail.